Lake Superior Basin, winter of 1854. While his neighbors rushed to complete standard log cabins before the killing cold, a French-Canadian trapper was still working, constructing something entirely different beneath the towering pines. His neighbors called it a luxury experiment. They called him a fool. Why waste time on some primitive shelter when proven log cabin design had worked for generations? Then January arrived with a vengeance. Temperatures plunged to -15 degrees for 6 straight days, the cold that would test every heating system in the territory. Standard log cabins failed. Families huddled around fires as interior temperatures dropped to the mid-30s. Ice formed on interior walls. But this trapper's foolish wigwam, it stayed 45 degrees warmer than their cabins. What did this quiet rebel understand about surviving winter that 2 centuries of frontier wisdom had missed? The accepted wisdom seemed bulletproof. Every trading post manual, every army field guide, every settler handbook recommended the same construction: 12 feet by 16 feet of hewn logs, each timber cut to 8 inches thick, chinked tight with clay and moss, topped with simple wood shingles or stripped bark. Build it fast, build it strong, survive the winter. Jacques Moreau had followed this exact blueprint when he raised his cabin that autumn, working alongside 3 other trappers who'd claimed adjacent sites along the ridge overlooking the lake. By December, the flaws emerged with brutal clarity. Moreau's cabin, built to standard specifications, leaked heat like a sieve. When outside temperatures dropped to -15 degrees Fahrenheit, his interior plummeted to 35 degrees by midnight, despite a roaring fire in the hearth. Frost glazed the single window from the inside. Cold air knifed through gaps in the chinking that had seemed tight during construction. Soot from the poorly drawing chimney blackened everything, forcing him to scrape creosote from the walls weekly. Worst of all, he burned through 3 full cords of split hardwood in just the first month, an impossible rate that would exhaust his winter fuel supply by February. The French-Canadian trapper working the site just uphill watched this unfolding disaster with growing certainty that another approach existed. Born in Quebec and raised in villages where winters regularly reached -30 degrees, he carried knowledge that extended far beyond standard frontier practice. His father had worked alongside Anishinaabe hunting parties in the Ottawa River country, and the son had observed their dome-shaped winter shelters, structures that seemed to defy logic by keeping occupants warm with minimal fuel. More recently, during 2 seasons working in Montreal, he'd apprenticed with Heinrich Müller, a German immigrant carpenter who'd brought old-world joinery techniques to the New World timber trade. Müller had taught him that proper construction meant understanding forces, wind loads, thermal bridges, moisture movement, rather than simply following established patterns. The German's workshop had been a laboratory of experiments, sapling frames bent and lashed with mathematical precision, mortise and tenon joints that locked without nails, clay mixtures that hardened to stone-like durability. Most importantly, Müller had drummed into him the principle that successful shelter design started with the environment, not the materials. When the trapper announced his intention to build a dome-shaped structure using bent saplings and bark covering, his neighbors responded with predictable scorn. The trading post foreman, a grizzled Scotsman named McReady who'd overseen cabin construction across 3 territories, declared it the most foolish waste of labor he'd witnessed in 20 years. "Everyone builds a cabin here," McReady pronounced. "You'll be cold and look foolish." The other trappers echoed this sentiment, questioning why anyone would choose primitive methods when respectable log construction had proven itself across generations of frontier settlement. Suppliers at the main trading post reinforced this skepticism. Why order birch bark and rawhide lashing when hewn logs and iron nails were readily available? The extra labor alone seemed prohibitive, bending green saplings into precise curves, peeling bark in sheets, gathering moss for insulation. Standard cabin construction could be completed in 4 days with 2 men. This dome experiment might require twice that time for a single occupant. But the trapper proceeded anyway, driven by a conviction that the conventional approach ignored fundamental principles. His first attempt proved partially successful and entirely instructive. Working alone, he erected a small dome frame using bent maple saplings, each piece carefully selected for flexibility and strength. The frame itself represented a marriage of techniques. Indigenous knowledge of sapling bending combined with Muller's joinery methods for creating rigid connections. At the base, he cut mortise and tenon joints where each sapling met the ground. Higher up, he used rawhide lashing soaked in pine pitch to bind the frame members together. The covering system drew directly from Anishinaabe practice he'd observed years earlier. Overlapping sheets of elm bark formed the outer shell, each piece positioned to shed water and wind. Inside, he lined the walls with peeled inner bark and stuffed the gaps with dry moss, creating what amounted to a primitive but effective insulation system. When December's first serious cold snap arrived, outside temperatures dropping to -12 degrees Fahrenheit with steady wind, his experimental shelter outperformed the neighboring cabins but fell short of his expectations. While Moreau's standard cabin dropped to 35 degrees inside, the dome maintained 42 degrees, a significant improvement but still uncomfortably cold for extended winter living. The trapper understood immediately where his system needed refinement. The insulation layer was too thin, the floor lacked proper isolation from ground cold, and the overall design required additional thermal mass to store heat between fires. More fundamentally, he realized that successful winter shelter demanded not a single innovation, but a coordinated system, each element supporting the others in ways that conventional cabin construction simply couldn't achieve. Standing inside his moderately warm but imperfect dome that December night, listening to the wind howl across the lake while Moreau cursed and fed more wood to his inefficient fire, the trapper formulated the principle that would guide his next phase of development. Indigenous knowledge, immigrant craftsmanship, and frontier materials could be integrated into something entirely superior to accepted practice, but only if he understood how site selection, structural design, insulation systems, and heating methods work together as a unified whole. The neighbors had called his first attempt wasteful. They were about to discover just how wrong conventional wisdom could be when tested against integrated traditional knowledge and systematic experimentation. The fundamental flaw in frontier cabin placement became starkly apparent during January's sustained cold spell. Every cabin along the ridge sat exposed to the prevailing northwest winds that swept unobstructed across 40 miles of frozen Lake Superior. These wind-driven convection currents didn't just make structures feel colder, they actively stripped heat from exterior walls through forced air movement that conventional chinking couldn't stop. Moreau's cabin, positioned prominently on the ridge's windward face to capture summer breezes and lake views, became a heat sink. Wind pressure drove cold air through every microscopic gap in his log walls, while simultaneously creating negative pressure that sucked warm air up through floor cracks and out through the roof. The trapper recognized this dynamic from his Quebec childhood, where village builders had learned through harsh experience that shelter placement mattered as much as construction method. But he also recalled something more specific from his observations of Anishinaabe winter camps along the Ottawa River. Their dome shelters were never positioned randomly. Instead, they clustered in natural wind shadows, behind rock outcroppings, nestled among dense stands of spruce, or tucked into slight depressions that broke the force of horizontal air movement. More critically, these indigenous builders understood entrance orientation. While frontier cabin doors typically face south for maximum daylight, Anishinaabe entrances always opened away from prevailing wind direction. This wasn't superstition, but applied physics. An entrance facing into the wind created positive pressure that forced cold air into the dwelling, while a leeward-facing entrance created a neutral zone where heated air could exit gradually without being sucked out by negative pressure. Heinrich Muller's carpentry knowledge added another crucial element to this site analysis. During their work together in Montreal, the German had explained how wind loading affected structural integrity. Any vertical surface exposed to moving air experienced not just cooling but physical stress. Muller had developed a technique called belt coursing, horizontal structural elements installed at regular intervals to prevent flexing and gap formation. In traditional German timber framing, these belt courses were heavy oak beams. But Muller had adapted the principle for lighter construction, using thin horizontal members to tie vertical elements together and prevent wind-induced movement. The trapper decided to test these combined principles through direct comparison. Rather than relying on theory, he would construct two identical domes at different sites and measure their performance under identical conditions. The first site matched conventional cabin placement, prominently positioned on the ridge's highest point for visibility and drainage. The second site incorporated indigenous siting wisdom, located 50 yards downhill in a natural depression surrounded by mature spruce trees with the entrance oriented southeast away from the prevailing northwest winds. Both domes used the same 14-foot diameter frame of bent maple saplings, but the trapper incorporated Muller's belt course technique into the structural system. At exactly 2 feet above ground level, he installed horizontal saplings running completely around each dome's circumference. These belt courses were lashed to the vertical frame members with rawhide soaked in pine pitch, creating a rigid horizontal ring that prevented the entire structure from flexing under wind pressure. The technique added only 4 hours of labor, but transformed the dome from a flexible shelter that moved with the wind into a rigid structure that resisted air movement entirely. For the downhill site, he added an experimental element drawn from his own frontier observations. Uphill from the dome, he constructed a windbreak wall using felled spruce boughs arranged in overlapping layers. The wall measured 5 feet high and 10 feet long, sized to protect the dome's windward face without blocking essential winter sunlight. The boughs were anchored with stakes and weighted with stones, creating a permeable barrier that slowed wind velocity rather than stopping it completely. This partial deflection prevented the turbulence that would result from a solid wall while reducing wind speed in the area immediately behind the barrier. The construction process revealed the practical challenges of implementing indigenous and immigrant techniques simultaneously. Building the leeward-sighted dome required careful coordination of 3 separate knowledge systems. The site selection followed Anishinaabe principles, but executing the dome construction in the confined space among the spruce trees demanded modifications to Muller's joinery techniques. Bending the frame saplings into precise curves became more difficult when working around existing tree trunks, while installing the belt courses required custom lashing methods to accommodate irregular spacing between frame members. When both experimental domes were completed in early January, the trapper began systematic testing that would definitively prove or disprove his integrated approach. Each morning, he recorded interior and exterior temperatures at both sites, using a mercury thermometer acquired from the trading post. He tracked daily fuel consumption by weighing the cordwood before burning. Most importantly, he documented wind conditions and their correlation with heat loss rates. The results exceeded even his optimistic projections. During a sustained cold spell, when exterior temperatures held steady at -18 degrees Fahrenheit for 5 consecutive days, the performance differences between sites became dramatically apparent. The ridgetop dome, despite its improved belt course structure, maintained interior temperatures of only 40 degrees, barely better than his original experimental shelter. Fuel consumption remained high at nearly 2 cords per week. Wind pressure flexed the structure constantly, creating microgaps that allowed heated air to escape. The leeward-sighted dome performed like an entirely different technology. Interior temperatures stabilized at 51 degrees, 11 degrees warmer than the ridge site, despite identical construction and insulation systems. Fuel consumption dropped to just over 1 cord per week, a reduction of nearly 50%. The windbreak wall created a pocket of relatively still air that eliminated the convective cooling effects plaguing the ridge site. More importantly, the reduced air movement allowed the dome's heating system to work efficiently rather than fighting constant heat loss. These measurements validated the principle that shelter performance resulted from environmental integration rather than construction technique alone. The same structural design produced dramatically different results, depending on site selection and wind management. Indigenous knowledge about microclimate selection combined with German techniques for structural rigidity had created a system that outperformed conventional cabin construction by substantial margins. The trapper now possessed quantified proof that challenging frontier orthodoxy through traditional knowledge integration could yield measurable superiority in winter survival conditions. Even with optimized siding solving the wind problem, the fundamental issue of heat conduction through the shelter envelope remained unresolved. The leeward dome's 51-degree performance represented a significant improvement, but the trapper understood that the curved sapling frame alone wasn't providing sufficient thermal barrier. Heat was still escaping through the single-layer bark covering and directly into the frozen ground beneath the structure. Standard log cabins suffered from the same conductive losses. 8-inch thick hewn timber still conducted cold through the wood grain itself, while end grain exposure at log joints created thermal bridges that channeled interior heat directly to the exterior surface. The solution lay in understanding insulation as a layered system rather than a single material application. During his observations of Anishinaabe winter camps, the trapper had noted that their most successful shelters employed multiple distinct covering layers, each serving a specific thermal function. The outer layer of birch or elm bark provided weather protection and structural integrity. Beneath this, they installed a secondary layer of inner bark, the fibrous material between outer bark and wood, which created air pockets when properly layered. Finally, dried moss filled any remaining gaps, functioning as what modern builders would recognize as blown-in insulation. Heinrich Müller's German carpentry knowledge contributed a crucial refinement to this traditional system. Müller had taught him that effective insulation required not just materials, but air gaps of specific dimensions. Too narrow, and air movement couldn't occur to equalize temperatures. Too wide, and convection currents would actually increase heat transfer. The optimal gap measured approximately 3 inches, wide enough to trap still air, but narrow enough to prevent circulation. This principle guided the trapper's development of a triple-layer insulation system that would transform his dome's thermal performance. The construction process began with harvesting materials according to precise specifications learned through trial and failure. Outer bark required sheets at least 2 feet wide and 4 feet long, peeled during late spring when sap flow made removal easier and bark remained flexible through winter storage. Inner bark demanded different harvesting. The cambium layer had to be scraped and processed immediately to prevent spoilage, then dried in thin sheets that could be layered like overlapping shingles. Moss collection followed Anishinaabe techniques. Only certain species retained insulation properties when dried, and gathering had to occur during specific weather conditions to ensure proper moisture content. Installation began with the outer bark layer, attached to the dome frame using a technique that combined indigenous and German methods. Rather than simply overlapping sheets randomly, the trapper created a systematic shingling pattern that started at ground level and worked upward. Each bark sheet was positioned with its grain running vertically to shed water, while horizontal overlap ensured no direct path existed for air infiltration. Attachment points used rawhide lashing reinforced with wooden pegs, a method that provided secure connection without creating puncture holes that would compromise weather sealing. The inner bark layer required entirely different installation methods. These fibrous sheets had to be positioned with their grain running horizontally, creating cross-hatched fiber orientation that maximized insulation effectiveness. More critically, the inner bark couldn't contact the outer bark directly. Doing so would create thermal bridging that would negate the insulation effect. Instead, the trapper used thin wooden spacers carved from cedar scraps to maintain the crucial 3-inch gap between layers. These spacers were positioned every 18 inches around the dome's circumference and secured with pine pitch to prevent movement. Moss installation represented the most technically demanding aspect of the insulation system. The material had to be stuffed into the cavity between bark layers using a density that maximized air trapping while maintaining structural integrity. Too loosely packed and settling would create gaps that allowed convection. Too tightly compressed, and the moss lost its insulation properties entirely. The trapper developed a testing method using a thin wooden rod to check density. Properly installed moss should compress slightly under pressure, but spring back when released. The floor insulation system required solving the ground contact problem that plagued both cabins and his earlier dome attempts. Direct contact with frozen earth created a massive heat sink that no amount of wall insulation could overcome. The solution drew from both indigenous elevated floor techniques and German foundation principles. Using split cedar logs as foundation posts, he constructed a raised platform 6 inches above ground level. The platform frame used mortise and tenon joinery to create rigidity without metal fasteners, while the flooring consisted of split planks fitted tightly together. Beneath this raised floor, he installed a ground insulation system that prevented heat loss through the earth itself. Cedar bark, chosen for its rot resistance and low thermal conductivity, covered the ground in overlapping sheets extending 2 feet beyond the dome's perimeter. Above this, a layer of dried leaves and moss created additional insulation, while the 6-inch air gap between ground covering and floor planks provided the final thermal break. The completed insulation system transformed the dome into a precision instrument for heat retention. When the trapper conducted his next round of temperature testing during a cold snap with exterior temperatures, holding at -10 degrees for 5 consecutive nights, the performance improvement exceeded all projections. Interior temperatures stabilized at 63 degrees, 12 degrees warmer than the previous best performance and 28 degrees above the neighboring cabin temperatures. More significantly, fuel consumption dropped to just 9/10 of a cord over the 5-day test period, compared to nearly 2 cords for the previous dome configuration and over 3 cords for standard cabin heating. The floor surface measured 55 degrees on winter mornings, warm enough for bare feet, while interior wall surfaces held steady at 48 degrees, even when fires burned low overnight. These measurements proved that systematic insulation design could overcome the fundamental thermal limitations of frontier construction. The combination of indigenous layering knowledge, German craftsmanship principles, and experimental refinement had created a shelter envelope that retained heat with unprecedented efficiency. The trapper now possessed not just a warm shelter, but a replicable system that challenged every assumption about winter survival in the northern wilderness. The superior insulation envelope had solved heat retention, but the trapper recognized another fundamental challenge that conventional frontier heating completely ignored: thermal storage. Standard cabin fireplaces and small wood stoves produced intense heat while burning, then allowed interior temperatures to plummet within hours once fires died down. This created a cycle of constant fuel feeding that exhausted wood supplies and required occupants to wake multiple times nightly to maintain fires. Even worse, the direct radiant heat from open flames created uncomfortable temperature gradients, scorching hot near the fire, freezing cold just feet away. The solution required integrating 2 distinct knowledge systems that addressed thermal mass from different perspectives. During his observations of Anishinaabe winter camps, the trapper had witnessed their hot stone heating technique, a method that seemed almost magical in its effectiveness. Camp builders would heat river cobbles directly in their fires during early evening, then transfer the stones to designated areas within the shelter where they radiated stored heat throughout the night. The stones typically maintained useful heat output for 6 to 8 hours, providing steady warmth long after the fire had burned down to coals. Heinrich Müller's carpentry knowledge contributed the engineering principles necessary to adapt this technique for permanent installation. Müller had explained how German workshops used thermal mass systems, large masonry stoves, and heated wall systems that stored heat from intense but infrequent fires. The key insight involved understanding heat capacity. Materials like stone, earth, and clay could absorb tremendous amounts of thermal energy during heating, then release that energy slowly over extended periods. This created steady, comfortable heating that eliminated the temperature fluctuations plaguing standard heating systems. The trapper designed a thermal mass system that merged these approaches into a single integrated solution. Along the interior wall opposite the dome's entrance, he excavated a foundation area measuring 6 feet long by 10 feet wide by 18 inches deep. This excavation allowed him to construct a thermal mass bench that would serve simultaneously as seating, sleeping platform, and heat storage system. The bench construction used locally available materials combined according to precise specifications developed through experimentation with different mixture ratios. The thermal mass consisted of 3 distinct layers, each serving specific heat storage and transfer functions. The foundation layer used river cobbles ranging from fist-sized to head-sized, selected for their density and heat retention properties. Above this, he installed a mixture of local clay, sand, and crushed stone that formed a concrete-like mass when properly proportioned. The top layer consisted of flat field stones fitted tightly together to create a smooth surface for direct contact. The completed bench measured 12 inches thick, sufficient thermal mass to store significant heat while remaining practical for construction and maintenance. Integration with the heating system required solving the challenge of efficiently transferring heat from fire to thermal mass. Rather than using an open fireplace that would waste heat up the chimney, the trapper installed a small cast iron stove acquired from the trading post. The stove measured 15 inches wide by 18 inches deep, sized to provide adequate heat output without overwhelming the dome's interior or consuming excessive fuel. More importantly, the compact stove could be positioned directly adjacent to the thermal mass bench, allowing efficient heat transfer through conduction and radiation. The stove installation incorporated Muller's technique for maximizing heat extraction from combustion. Rather than venting the stove directly through the dome's smoke hole, the trapper constructed a heat exchange system using clay pipe sections that snaked across the surface of the thermal mass bench before exiting through the roof. This serpentine flue path forced hot exhaust gases to travel across the thermal mass, transferring heat that would otherwise be lost to the atmosphere. The clay pipes were embedded into the bench surface using a mixture of clay and crushed brick that provided excellent heat conduction. Muller's stove jacket technique added another layer of heat capture to the system. The trapper encased the cast iron stove in a custom-fitted jacket made from the same claystone mixture used in the thermal mass bench. This jacket measured 3 inches thick on all sides except the fire-loading door, creating a thermal flywheel that absorbed heat from the stove's metal surfaces and radiated it gradually into the dome's interior. The jacket also incorporated the indigenous hot stone technique by embedding specially selected flat stones into its surface, stones that could be heated by the stove's operation and removed for targeted warming applications. The seasonal adaptability system addressed the challenge of temperature control as winter progressed into spring. The trapper had observed that fixed heating systems often became uncomfortably hot during temperature swings, while remaining inadequate during extreme cold snaps. His solution involved constructing removable sections in the dome's outer bark layer that could be opened or closed depending on exterior conditions. These sections functioned like adjustable vents, allowing precise control of interior temperature without compromising structural integrity. During February's sustained cold period, when exterior temperatures averaged minus 12 degrees, with nighttime lows reaching minus 22 degrees, the integrated thermal mass system demonstrated its superiority through measured performance data. The trapper recorded evening thermal mass surface temperatures of 102 degrees after 2 hours of intense stove firing. By morning, with the fire completely extinguished, the bench surface still measured 72 degrees, providing comfortable radiant heat throughout the night without requiring fuel additions. Interior air temperatures remained remarkably stable, ranging between 60 and 67 degrees throughout the 10-day test period. Fuel consumption dropped to just 0.6 of a cord over 10 days, compared to neighboring cabins that burned 1 8/10 cords during the same period. More significantly, the thermal mass system eliminated the temperature fluctuations that made standard cabins uncomfortable, no scorching heat near fires followed by freezing cold hours later. The system had transformed winter heating from a constant struggle against heat loss into a controlled process of heat storage and gradual release, proving that indigenous knowledge combined with immigrant engineering could create heating technology superior to anything available through conventional frontier construction. 6 years of gradual refinement had transformed the trapper's experimental shelter into a proven system, but winter of 1860 delivered the ultimate test that would either vindicate his integrated approach or expose fatal flaws under genuinely life-threatening conditions. The storm system that developed over Lake Superior in late January combined multiple destructive elements: sustained temperatures dropping as low as minus 35 degrees, wind gusts reaching 50 miles per hour, and lake-effect snow accumulation that would challenge every structural assumption about frontier building. The blizzard's intensity exceeded anything in the region's recorded history. Snow fell continuously for 12 days, accumulating in drifts that measured 5 feet deep against vertical surfaces. More dangerously, wind-driven snow created compression loads that standard cabin roofs were never designed to support. The combination of extreme cold and structural stress would test not just heating systems, but the fundamental engineering principles underlying different construction approaches. Conventional log cabins began failing within the first 48 hours of the storm. Jacques Moreau's cabin, already struggling with heat loss throughout the winter, suffered catastrophic roof damage when accumulated snow exceeded the load capacity of his wood shingle covering. The roof structure, built according to standard Frontier specifications using 2-inch thick rafters spaced 24 inches apart, couldn't distribute the concentrated weight of wet, wind-compressed snow. When the roof partially collapsed, it compromised the cabin's structural integrity and created massive heat loss through the damaged covering. 2 other cabins in the immediate area experienced similar structural failures, but the consequences extended far beyond property damage. With roofs compromised and heating systems failing, interior temperatures in the damaged cabins dropped into the high 20s, well below the threshold for safe human habitation. One occupant suffered severe frostbite on his extremities, requiring emergency evacuation to the main trading post 20 miles away. The evacuation itself proved costly and dangerous, requiring a specially equipped dog sled team that charged 4 times the normal transportation rate due to the extreme conditions. The fuel supply crisis that developed during the storm's second week revealed another critical flaw in conventional cabin heating. Standard log cabins, already consuming nearly 4 cords of wood per month under normal winter conditions, required even more fuel during the extreme cold snap. When exterior temperatures held at -30 degrees for 6 consecutive days, cabin heating systems demanded continuous firing that exhausted stockpiled fuel supplies. Emergency wood delivery from the trading post cost 3 times the normal rate, while transportation delays meant some cabins went without adequate fuel for crucial periods. The Trapper's dome system demonstrated its engineering superiority through measurable performance under these extreme conditions. The curved structural design distributed snow loads evenly across the entire frame rather than concentrating weight at specific points, like conventional peaked roofs. When 5-foot snow drifts accumulated against the dome's windward face, the structure absorbed and redistributed the load through its integrated frame system. The belt course reinforcement installed years earlier prevented the frame from flexing under the additional weight, while the curved profile allowed wind to flow over the structure rather than creating pressure points that could cause structural failure. More significantly, the thermal mass system proved its value during extended periods when firing the stove became difficult or dangerous. During the storm's most intense phase, when venturing outside to gather fuel posed serious risks, the trapper could heat his thermal mass bench to maximum capacity during brief calm periods, then rely on stored heat for up to 12 hours without additional firing. This capability eliminated the desperate fuel feeding cycle that plagued cabin occupants who were forced to venture out in dangerous conditions multiple times daily to maintain fires. The dome's seasonal adaptability system, designed for temperature control during normal winter conditions, became crucial for managing extreme weather variations. When wind-driven snow began infiltrating through standard cabin chinking, the trapper could adjust his dome's ventilation and insulation configuration to maintain interior conditions despite external chaos. The removable bark sections allowed precise control of air circulation, preventing both overheating during intense firing periods and dangerous heat loss during fuel conservation phases. When the storm finally broke after 12 days, the performance contrast became starkly apparent through direct measurement and observation. The trapper had maintained interior temperatures averaging 60 degrees throughout the crisis, never dropping below 55 degrees even during the coldest nights. His fuel consumption totaled exactly 1 cord over the entire 12-day period, less than 1/3 the amount consumed by undamaged cabins during the same period. Most importantly, his shelter required no repairs, no emergency resupply, and no evacuation support. The aftermath of the Great Blizzard transformed regional attitudes toward alternative construction methods. McReady, the trading post foreman who had initially dismissed the dome as foolish experimentation, visited the site personally to document what he observed. Standing inside the warm, structurally sound dome while surveying the damaged cabins scattered across the ridge, He asked for detailed drawings and construction specifications. Within weeks, the trapper found himself conducting informal workshops for other trappers and camp supervisors, who recognized that conventional wisdom had failed catastrophically when tested by genuine crisis conditions. The knowledge transfer process revealed the challenges of scaling traditional techniques beyond individual application. Teaching the integrated system required not just construction methods, but understanding of environmental principles, material selection criteria, and seasonal adaptation techniques. The trapper developed a systematic documentation approach, creating detailed sketches that showed frame construction, insulation installation, and thermal mass configuration. More importantly, he emphasized that successful implementation required understanding the relationships between different system components, rather than simply copying individual techniques. By 1870, sapling frame dome construction had spread throughout the northern Great Lakes trapping and logging region. Camp supervisors began specifying low-profile bark-covered shelters for winter work crews, while fur trading companies included dome construction techniques in their operational manuals. The method's adoption wasn't universal. Many operations continued using standard cabin construction, but alternative techniques were no longer dismissed as primitive or impractical. The trapper's quiet revolution had demonstrated that challenging conventional wisdom through systematic integration of traditional knowledge could produce measurably superior results under real-world conditions, establishing principles that would influence cold weather construction practices for generations to come.